All right. Can everyone hear me? Welcome to Astronomy Clubs of New Jersey. We are here in Jenny Jump State Park in Hope, New Jersey. I want to thank you all for joining us. I know we're very excited to have you guys. I believe you all were scouts or a school group. Ooh, a homeschooling group called Barefoot University. Perfect. But I do want to welcome you guys here to UAC&J for this special presentation. A couple things as we start. If any of you guys need to use the restroom, that would be the porta potty in the back. It is illuminated by red for ease of finding in the dark because this is a state park and it does in fact get quite dark. We are one of the darkest sites in publicly accessible in the state of New Jersey, which makes it a perfect place to do the astronomy outreach that we do. In addition, as many of you may have seen, we have a little museum and gift shop area available. We have a meteorite display and a whole bunch of cool stuff to see in there. I know we have a number of volunteers who have either brought their own telescopes or who have opened up various observatories, because each of those sheds out there houses its own scope, and the ones with the roof rolled off are open and have a volunteer manning that, so you'll be able to ask questions, see what they're looking through in the scope, and see for yourselves through the telescope. For the adults here, please use your headlights when you leave. We're not a big fan of becoming roadkill and run over, so let's keep that record to 0. For going back to the fact that it is dark, if we have flashlights and we're trying to use that to get around, I just ask that we keep those lights pointed towards the ground. We don't need to accidentally blind people by having as much as the cool flashlight rays are neat to see, they are also very blinding for those who are not prepared for them. So, like I said, lights towards the ground. With that, you're not here to hear me blabber on. You're here because Paul Fischer has agreed to give a presentation, and I believe he's going to let you choose your own astronomy adventure tonight. But a little bit about Paul. Paul has a Bachelor in Engineering in Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. He's always been interested in space, and his official start was being very uncomfortable on his roof. We don't ask how he got on the roof. It was probably not parent approved. But he found the Galilean moons of Jupiter, and since then he has put anyone here's to be read pile to shame with the amount of books he has read about space and astronomy. And he's often found volunteering here and is an active member of one of our member clubs, Northwest Jersey Amateur Astronomers, and is currently our vice president here. I think that about covers it.
It does cover it. Thank you, Kim.
Cool.
Hello, everyone. Welcome. Oh, and my... It's probably telling me that I forgot to plug the power in. So let me rectify that right away before we lose it completely.
This is the opposite problem of have you tried turning it off and back on again. You should unintentionally turning it off is usually a problem as well.
There we go. Okay, so now that it'll stay on for the presentation, I just want to point everyone, first of all, hi and welcome everybody. Just want to point out we already looked at, whoops, let me not use that particular, that's a little bright. At this comet right here, we already looked at this comet. That's Comet Lemon. You may have seen that in my telescope, one of my personal telescopes that I bought up here tonight. It's southeast of the Sunflower Galaxy. It's near the handle of the Big Dipper, as everyone saw. It's probably gone and set by now. This is the right ascension and declination. And if anyone's ever heard of longitude and latitude, that is a coordinate system for the ground. The right ascension and declination is a coordinate system for what we call the celestial sphere above us. And of course, it looks like that the sky is moving across from east to west every evening and during the day too, right? The sun and moon move in the same direction. You can see those during the day. Sometimes the moon, but always the sun. And then that coordinate system, right ascension and declination, is actually on that celestial sphere. But of course, that's not really moving, because those stars have remained there for as long as there have been people, and longer than that, much longer. But it looks like it's moving, so we use the right ascension and declination, and we put it on the sky so that it's still the coordinate system makes sense while it's moving across the sky. And Comet Lemon, like I said, is probably gone now. It sets around 8 o'clock, so we probably can't see it, but we might see the other one later on in somebody else's telescope. So Kim was right. I'm going to give you a choice on what presentation you want to hear. However, I would say that my presentation on black holes and on what a star is made of, and what you can see about a star and understand about a star might be a little technical for the younger people. So I'm going to recommend that we either do a introductory to the various parts and what you want to understand when you're looking at a sky and what a telescope does. So there's that one. And then there's one that I called Nope, which is a presentation about debunking some of the conspiracy theories associated with astronomy versus astrology and flat Earth and those type of things. Which do you feel might be more appropriate? I will go with the introductory one unless somebody tells me different. So you let me know if you want to hear the other one. All right, so it's split right down the middle. I'll tell you what. I'm going to do the introductory one, and you stop me if you think this information is all stuff that you know that you already know and you don't want to hear about again. How about that? All right, so here we go. File Explorer and my documents, presentations, and so you bought a telescope. Here we go. And it's coming up on my PowerPoint. And here we go, slideshow from the beginning. There you go. You bought a telescope. Now what? So this is, you've already done the research and you already have a telescope. Some of you might have some hobbyist telescopes, some of the ones that are about $100-200. This is for a little bit telescopes that are a couple of hundred to under 1,000 still. So it's just your first telescope. It's a good telescope. You can see some really cool stuff in it. But now what do I do now that I have this thing? How does it work? How did I find the comet over there with somebody was asking whether my telescope tracked the comet by itself, and some of them do, but you don't have to use those. You can know this stuff and do it yourself. So the intelligence is here instead of in the telescope. It's a little harder and it's a little slower, so that's why the automatic telescopes exist. But all right, so I wanted to show here we have a companion. Dan Kirby gives another talk on how to choose a telescope. So we have a companion presentation. A war story already. I think Kim mentioned that I went up to the roof of my house. It wasn't as dangerous as it sounded. There's a door to access a flat portion of my roof.
That's what everyone says.
But this is Jupiter, and 1, 2, 3 stars along the equatorial plane of Jupiter, and another star here aren't really stars. What are they? Moons. It's in fact the Galilean moons, and I could see this in a pair of binoculars that I dragged up onto my roof. So you don't need a telescope. You just need to know what you're looking at. All right, and there's a shiver of realization. This is important. You're going to learn things as you get older, and some of you might be old enough already, like Isaac Newton and Galileo and Kepler and Copernicus. Okay, and Newton famously said, "If I have seen further, it is by standing on the shoulders of giants." That means that he took information from other people, other scientists who have gone before him, and his contributions plus their contributions came together to bring some of our modern physics that we're still using now. All right, Einstein and others have the big accolades nowadays, but Sir Isaac Newton invented calculus and the laws of gravitation and a whole bunch of general mechanics for physics and a whole bunch of other things, and he did it by looking at the stars, and he did it by knowing science and adding his own very significant brain to what we already knew. And we can appreciate that, the fact that he learned that stuff and he observed it just by looking at the stars, because that's what inspired him to come up with these ideas. So there's a point to that story. Why is it pertinent? Well, we have to understand what I talked about a little bit earlier, that celestial sphere above us. We know that now that the Earth is spinning, and we're standing or sitting on the Earth or lying down on the Earth right now, and it is spinning beneath the sky. However, we use a model in our brains because when we look up, it looks like the sky is moving from the east to the west, when we're actually spinning underneath the sky from the west to the east. So, but we use that model in our brain that the sky is moving across from east to west. That model is wrong, right? That's not what's really happening. We're spinning. The sky is sort of staying there, at least as far as we can observe with our eye. But the model's useful in our understanding of how to track things in the sky. And that's called a model. And it's very important that you realize that many things we do are models. That's not really how it's happening. It's more complicated than that. But the model helps us understand it and make predictions. That's why amateur astronomy is really, really cool. It's teaching us about science. It's teaching us about models. It's teaching us about how science is built upon the work of other people. It's seeing the history. Those are all cool things about astronomy. All right, sniffing the models. A model is a simplified representation of an imagined reality that enables predictions to be developed and tested by experiment. Science, that's a definition from Science Learning Hub. Science, philosophy, religion, etc. universally agree that humans exclusively use models to understand reality, right? That's a little bit of a joke. If you've had any philosophy ever, you realize that the normative view of philosophy is versus more reality-based philosophy is a debate that's been happening amongst philosophers forever. And here's the celestial sphere, what I talked about. This is the Earth right here, the blue dot. And we're sort of thinking about the sky as this sphere that all the stars and planets and everything are on, and it's moving overhead. And we put the coordinate system. There's the coordinate system. Those are the grid lines. They look like longitude and latitude. We put it on the sky. We called it right ascension and declination. And the North Pole for the Earth corresponds to the North Celestial Pole. South Pole of the Earth corresponds to the South Celestial Pole. And then the equator for the Earth is here, this blue. And the red is the ecliptic plane. So let's talk about that. The equator we know. We're familiar with the equator on the Earth. You just project it into the sky. That's it. However, what is the ecliptic plane? What is that? It looks like it's tilted. Like what's tilted about the Earth? The axis of rotation. So what's really happening is the north and south aren't straight up and down. They're sort of tilted to where the sun is. And that's 22 degrees, and that's this angle right here, this ecliptic plane. And it isn't just the sun and the Earth, but it's all the planets and the moon and basically everything in the solar system. You can find it all along this ecliptic plane. If you follow the sun in an arc in the sky and the moon in the arc in the sky, that same arc has all the planets, all the asteroids, all those type of things. So that celestial, ecliptic plane is very important for identifying things in the sky. If you see this bright object here that might be Saturn, and it looks like it's following the arc in the sky that the sun and the moon are, you can think, oh yeah, that's probably a planet and it's not a star because it's in the ecliptic plane, it's pretty bright, and we know all the planets follow the ecliptic plane. And here it is, so here it is with the poles straight up and down. And here it is, here's the sun, here's a planet that we're interested, and here's how it might actually look in space. I actually cut these out myself. They fell apart, so I took pictures of it now. But that axis is about 22 degrees in a tilt. And you can see we're looking this way because it's nighttime this way and it's daytime this way, right? It's nighttime this way. We're looking this way, and this planet looks like it's a little bit lower than the equator. It's along the ecliptic plane where the solar system is. And what's interesting is that the sun here is high in the sky because this is the equator. The sun is up here compared to where the equator is. If we go to the other side of the sun, where the northern hemisphere, the pole is tilted away from the sun, here is the equator. The sun is now low in the sky, right? Because here is the equator, the sun is low, but the planets are now high in the sky at night. So that's what's happening with the ecliptic plane, with the equator, and with the seasons. And this is the northern hemisphere, right? If we were down south in Australia, it would be reverse of what I just showed you. All right, another new thing to understand is that amateur astronomy is big because what did I show you? What's the difference in time between this and this configuration? Very good. Whoever just yelled 6 months, you get a star. And so 6 months. So how long does it take to see everything in the sky? Minimum. A year. So you can't start astronomy and then figure everything out in less than a year. Okay? And it's going to take you a long time longer than that because there's a lot of things to understand. And of course, if you want to see everything in the universe, it's going to take you a really, really long time, like forever, because there's lots of things in the universe. All right, let's talk a little bit about the telescopes, some of which you saw tonight. You saw my telescope, which I'll show you in a moment, but this is more like this telescope's going to be open. It's the far one on the left this evening in the observatory buildings. This is a refractor. It's got a lens in the front and a lens in the back, and people understand that pretty well. That's what a pirate telescope works like that. The light comes in here, and it has a focal point. Once it reaches this lens, these lines start to converge, and they converge right here. And then this lens also converges right here. It sees this image and then rebends it to your eyes. And as long as these two focal points line up, then you're going to see a clear image. If they don't line up, it's going to be, I didn't understand you, but if you, it could be a double image. That typically happens like during daytime when there's a lot of extra light around. But what happens if it's not exactly lined up? That's what you're doing when you're adjusting the focus on anything. You're actually taking the objective lens and the eyepiece focal length, and you're lining them up so they're exactly the same length and they line up on the same object. Does that make sense? All right, here's the Newtonian. Here's the telescope that I had that you saw the comet with earlier. And what happens there is the light comes in, it hits not a lens but a mirror. It bounces back, hits another mirror, and then goes out the side. Remember, the eyepiece was on the side, right, everybody? Okay, so that is a Newtonian. You don't have to have a curved lens. It can be a curved mirror. It's doing the same thing. It's focusing the light on a specific point. It then hits this mirror, and then this is a lens here. So this focal point and that focal point have to line up in order for it to be in focus. And this is a catadioptric. It's a Schmidt-Cassegrain. You don't have to remember that name. But this has mirrors too, except the light comes in, hits that mirror, hits this mirror, and instead of going out the side, it goes out the back. There's a hole through this mirror. Now here's an interesting question. Why is this mirror, which looks like it's in the way of the light coming in, and this mirror, which looks like it's in the way of the light coming in, why don't we see that in the image when we look through the telescopes? Because the same reason why I can look at the star, or I'm looking at Saturn right now. I can see Saturn here, but I can also see Saturn here, and here, and here. So all the light coming from very distant objects is traveling in basically a parallel path. It looks like they're straight. All the light coming in from those objects is straight. So all those objective mirrors or lenses see all parts of the object. Now, if the object was really close, then you might be able to detect the secondary mirror there. However, none of these things are close. Millions of miles away or millions of light years away even. What is a telescope's purpose? A telescope's main job is to make small objects that are far away bigger. Is that correct? That's one job. That's an old movie. I hate to say that that's an old movie because to me that doesn't seem like an old movie, but it's an old movie now. That is a famous line from Star Wars. It's a trap. That's what this guy's saying, and I made a trap for you guys. I apologize. So, is the telescope's main job to make a small objects that are far away bigger? It's only half the job. The other half of the job is that it gathers light to make objects that are dim bright. I can see way more stars in a telescope than I can see with my naked eye, because what it's doing is it's gathering way more light from that object. So here's the radius of my pupil. And everybody's pupil is about the same, about 3 millimeters. A 4-inch telescope is about 51 millimeters, and an 8-inch telescope is 101 millimeters. That's a lot more millimeters. Okay, and it has the radius squared here. It varies by the radius squared, and all I did was divide by the radius 9 by this number by 9, this number by 9, and that's the ratio of the amount of light, that's the surface area. That's the amount of available area to collect light that the telescopes, or your eye as a light gathering object, can gather. So 300 times for a 4-inch telescope, over 1,000 times for an 8-inch telescope. That's incredible. It makes things 1,000 times more bright. All right, and here is, we mentioned here that there's two lenses. There's the objective lens, or the objective mirror. And then there's the object on the end that we look through, and that is called an eyepiece. And these are the various types of pieces. You can get a whole bunch of different ones, and the thing to remember about that, there's a lot of information there. You don't have to worry about all that information. 2-inch versus 1.25 inches, that's there. The focal length we talked about, it's expressed in millimeters and is printed right on the eyepiece. This stuff is actually not that hard. I just listed it all here. However, what you do need to know is that it's a complicated little device. They're relatively expensive. You get some beginner ones with your telescope when you invest in a good telescope, but a good eyepiece might be around the same price as your telescope was. And so if you want to expand your ability to see objects and use different eyepieces, just keep that one in mind, that investing in an eyepiece is going to be additional significant expense. This Barlow here helps you with that. It multiplies or divides the eyepiece focal length by a set number that it's designed for, and it will effectively, if you have a Barlow, now you have 2 times the amount of eyepieces that you had before, because each eyepiece now the Barlow will do something to that focal length. Some other terminology: exit pupil, eye relief, apparent field of view, and true field of view. Just remember that there's a lot of terminology to learn about using some of these things, and so you might need to investigate that terminology when you're making decisions on a scope. So here's the other thing about a telescope. My telescope wasn't floating in air, was it? No, it wasn't. It was riding on something. There's 2 types of mounts. And you saw how my telescope moved, right? I moved it up and down or left and right so that people could see the comet through the telescope. That's called altitude azimuth. You'll see the scopes in the buildings there, they're equatorial mounted. They're a little bit harder and more sophisticated to set up. You have to point them at the North Star precisely. actually the North Celestial Pole, which is just a little bit off the North Star. So you have to figure out how to do that. It's called alignment. But once you do that, it's very easy to track anything in the sky because it follows that plane that I mentioned before. What's that plane? The ecliptic plane. The ecliptic plane. And you can get push and go to. So my telescope, the one you saw there over there, it's a pretty good beginner telescope. It was less than $1,000. And push and go to, I have a go to telescope at home that I didn't bring tonight, and a little bit of beginner astrophotography equipment, and that was more in the $3,000 to $4,000 range. Other accessories you might need: red flashlight, red dot finder. You saw my green laser pointer, everybody? Yeah, that's very helpful. A filter, a case, and a bench or chair. Everyone remember sitting down on my bench there? That helps you stay steady so you can see through the telescope better. All right, vision tips. What you need to know about your eyes and the darkness. You need 30 to 45 minutes for full adjustments of rod cells. That's just biology, and that's why we want you to point your lights down on the ground when you can, so you don't ruin anyone's night vision, because it takes 30 to 45 minutes to get it back all the way. Averted vision. Everyone knows looking out of the corner of your eye, right? You can still see stuff. Did you know that at nighttime you can actually see stuff better out of the corner of your eye than right straight on? That's because the rods are located around your peripheral vision. That's the corner of your eye. And the cones are located around the front, or the front facing, or say around the pupil in your eye. So night vision is better. They call it averted vision. You're looking sort of out of the corner of your eye when you're looking at objects through a telescope or at night. Motion helps. So if you move a little bit when you're looking through a telescope, you might actually be able to detect a dim object better. And then surface brightness. If you're looking through a planet, or looking at a planet or a nebulous object, something that isn't a point of light like a star is, then just realize that the more you focus in on it, the less light you're getting through the telescope. So it might be harder to see once you start really magnifying the image on dim objects. All right, learning the scope. First thing you did is, remember I was pointing in the sky and I was pointing out the Milky Way and the, what was that triangle called? The summer triangle in the sky, right? So in order to start appreciating the scope and where everything is in the sky, you kind of need to know where things are in the sky, right? So you want to start looking at the sky maybe without the aid of a telescope. Then you can use some navigation aids. Realize that your brain cheats a little bit when it's trying to learn things. And then come to things like this, sky parties and other events where you get introduced to all these types of concepts. Here's some navigation aids. This is called a planisphere. We actually have some in the museum area that you can maybe take a look at. Star atlases in the written form. This is 6th magnitude. That is a star that is relatively bright. You can see them with your naked eye, no problem. 11th magnitude. There's a lot more stars up there that we can't see, that are very dim. They get even dimmer than 11th magnitude, but look at the amount of difference in, this is a little book, a thin booklet, and this is like an encyclopedia's worth of stars. So the dimmer you get, way, way more stars. The other thing you want to take a look at it, what's wrong with this planisphere? Take a look, north and south look good, take a look at the other one. Are wrong. That's correct. They're wrong for something, though. They're wrong for the ground, which is the map. When we're looking at a map, it looks like we're looking down at the ground. North, south, east, west. That's fine. North, south, east, west, but I'm looking down. Now I'm going to look at the celestial sphere above me. Okay? And I take this one, and I look at it, and I point at the ground, and it's wrong if I'm pointing it at the ground. But if I'm pointing it at the sky, where the things that I'm actually looking are, now east and west line up the way they're supposed to. So keep in mind that when you're looking at celestial references, printed celestial references, east and west are going to be reversed because you're not looking at the ground, you're looking at the sky. So east and west are going to be reversed. And of course, there's everyone's favorite apps. Two that I use all the time are Stellarium and Sky Atlas, and there are many others. Objects, things that you can see in the sky. Maybe we'll see some of them tonight. I think the moon's going to be up very late because it's almost a new moon. Some of the planets are up tonight. We talked about what one's definitely up tonight? Saturn, good, you're going to see it. Stars, some deep sky objects, outer planets and asteroids, and then transient objects. We saw one tonight already. What was it? A comet. We saw a transient object. What transient means is that it's not always there. It's here now. It's going to be gone later. The stars, if you come up here, and then we talked about Vega, if you find Vega, and then you come back next year at the exact same time, it's going to be in the exact same place. So the stars will always be there at the same time, at the same date. The transient objects won't always be there. There are different catalogs. There's the Messier catalog and the NGC catalog, and here's some information about it. What's interesting is that the Messier catalog was developed by a comet hunter named Charles Messier. He lived from 1730 to 1817, so a long time ago. And the catalog is interesting because everyone uses it to find the first cool deep sky objects in the sky. But Charles Messier didn't want you to look at them. At least he didn't want fellow comet hunters to look at them because they were looking for comets. And these Messier objects was a list of things in the sky that were not comets, so don't look at them because they are not comets. Okay, but ironically, we use that catalog very frequently to look at those objects in the sky. And then the NGC IC catalog, which is famous. It was originally compiled by John Lewis Emil Dreyer, but it was based work on a famous astronomical family, the Herschel family. Some stuff that you can see in the sky. When you're looking at the moon, you can start to see detail. Now, this is one of my first pictures of the moon. I just held up my cell phone to the telescope that you saw out there. And look at that detail already. You can see the seas. You can see craters. Kind of cool, right? We unfortunately, like I said, I don't think we're going to see the moon tonight because it's close to a new moon. You can see the magnitude. Look at these stars here versus this star. This one's really bright. The other ones are not. So you start to get the idea differences in light coming from different stars. That's how scientists know the properties of stars. And you can see here, this one's kind of orange, yellow, and this one's kind of blue. Stars have different color light. I'm sorry? You are, wow. Okay, we have a junior astronomer over there. Correct, just like a flame, right? What's that stuff called that you're seeing? Plasma. Plasma. It's a different state of matter. Like gas, liquid, solid. Plasma is a different state of matter. Outer planets, disk resolution. So this is you can see these stars, and you can see this one's very big, but that's because it's bright. And these ones are very big, but that's because they're also bright. But this isn't very bright, but you can actually see that it's a circle, not a point of light. So I know it's a planet. It's called resolving the disk of the planet. I can see it's a circle, not a point of light. Everyone's favorite subject, math. And you don't have to memorize any of this stuff, but you have to do some simple math. To understand the magnification, you need to know the focal length of your telescope and the focal length of the eyepiece. Like I said, the focal length of the eyepiece is printed right on the eyepiece, and if you bought the telescope, you have the specs for the telescope, so you know that focal length. True field of view is just simply the published actual field of view, apparent field of view of your eyepiece divided by the magnification. So that's not that hard, it's just a division. And then now you have all the math you need to create an eyepiece chart for your telescope. And what does that mean? Look at this object. This is a nebulous cloud in the sky I want to look at. And this is what I see through my telescope. I want to make sure that I can see the whole object. And so I need to know what that radial size is. So I need to know how big my field of view is versus the object. And these equations will help you figure that out. You don't have to memorize them, like I said, but know that it's a very simple mathematical relationship, and you can figure that out. And then coordinate system madness. We talked about the coordinate system, azimuth and altitude versus right ascension and declination. Just realize the terminology is very similar, but they're different coordinate systems. And so they don't define the various terminology the exact same way. So just realize altitude and azimuth, right ascension and declination. You might want to look that up for a little additional help if you're just starting to understand the difference between the coordinate systems. One more technique we'll talk about tonight. You're not going to be able to avoid it completely. You'll learn the sky much better. It's fun. So if you buy a go-to, they can steer to the various objects all by themselves, but they have to first know where they're pointing in the sky. So you still have to find stars in the sky to finish doing your alignment. You've aligned it to the North Star, but now you have to point to 1 or 2 stars or even 3 stars in the sky and tell the telescope these are these stars. And now it'll understand where everything is in the sky. And so you still have to know a little bit about where the stars in the sky by yourself before the telescope can help you find things. And here's Bob, an imaginary constellation. And Bob is an accountant. And right here we want to find this object. We'll call it M401K because he's an accountant. And here is our field of view in the telescope. So we can find this bright star and we put our telescope on it. But now how do we find this object that we want to take a look at? We walk the telescope up. We move the telescope so we see this star, and then we see this star, and then we move it down a little bit this way, and then now we can see the object. That's called come on, Paul. It's called star hopping. There it is. Sorry. And here's an actual example of a real object that you could star hop to. It's one of the simpler ones. This is the star Vega, and we talked about finding Vega. We could see it immediately. We can point our telescope at Vega, and we star hop along this this shape here. Who can tell me what this type of shape is called? That's a parallelogram. We take a look at Vega, and then we star hop from here to here, and right here is the Ring Nebula in between these two stars. So if we go from here, and then we move the telescope here, and then here, now we can find the Ring Nebula. Star hopping. few more things. Here's some homework. Now, definitely these are not these are reference books. However, this one you can actually read through. It's a good primer, and 365 Starry Nights by Chet Ramo. I highly recommend that for anyone who's beginning their journey in amateur astronomy. So you can read that one all the way through. The rest are more references, so don't read through the. But there is plenty of help available if you have interest. And like I said, it's a very partial list, but these are some of the ones that I myself have used and or read through. Certainly join an astronomy club. Just another, that's another way to learn, by the way. If you are geeking out with a bunch of fellow geeks, okay, some of that smart runs, rubs off of them onto you, and that's very helpful. The other astrophotography and EAA is a whole nother subject, and I'm not going to really cover it at all. However, the other really effective way to gather light is not only do you have that aperture, that 8-inch, remember gathering 1,000 times more light than your eye can, but you can increase the amount of exposure using photography. A camera has a length of exposure, and of course the longer you expose your images to the light, the more light you will gather. So it's another way of making dim objects start to appear with their details. Electron EAA is another form of astrophotography. It is like the Polaroid camera of photography. For astrophotography instead. It's called electronically assisted astronomy. And you are here, there are people even tonight that are skilled astrophotographers here, so you can ask some questions. And here's some pictures that I took that are EAA. That is a crystal ball nebula. That is the Whirlpool Galaxy. There's a better picture I took of the moon. There's Saturn itself, and you're going to see Saturn a little bit different. You're going to see it with, instead of the rings like this, at a, I'm going to use a technical term, oblique angle. You're going to see it right, it's called edge on. You're just going to see it right like the rings. Say you take a plate, you can look at the plate from the top down and you see a big circle, or you can turn it so that the side is facing you and it looks like a straight line across. And tonight it's going to look like a straight line across. It's called edge on. This is Caroline's Rose. This is an open cluster of stars. You can sort of see a rose-like pattern in there, right? Kind of cool. This is the Intergalactic Wanderer. This is a globular cluster that is extremely far away. It's like 60,000 light years, something in that range, 45, 60, something in that range. They didn't think it was actually part of our galaxy. It is actually part of our galaxy originally when they found it. This is the Ring Nebula. You'll probably see that one tonight, M57. And that was it. So we're going to take any questions. And
right, because thank you, Paul, for a great presentation. Because I trust everyone to kind of know how lines work. I have a microphone here, so if you have a question, you can come up to the microphone. I think I have it set where most of you can speak into it without problem. Unfortunately, adults, if you have a question, you're going to have to get a little bit lower to the mic. But have at it. Yep, come up to the mic and...
How many light years away is the sun?
How many light years away? Yeah, it's like, ooh. Yeah, I don't remember the definition of how many light years. I think it's like point, oh, it's tiny. It's like 0.00 something, I think.
Considering
However,
it's 8 minutes for light from the sun to get here, I
yeah,
would think it would be like 8 light minutes.
it's 8 light minutes. So, however, so you divide the 8. You divide how many minutes there are in a year, and you divide that by 8, and that's how many light years. So 365 times 24 times 60 divided by 8, whatever that number
Or
is.
just remember the number from the song in Rent. Apparently that has a fun.
So very small amount of light years, but interestingly, I can tell you how much it is in miles. It's about 393 million miles away, and I can tell you how many astronomical units it is away. It's 1 astronomical unit, and when you see 1 appearing naturally in science, you might begin to think that that's the definition of what an astronomical unit is, and that is. So the distance from the sun to the earth is about 1 astronomical unit, because that's how you define astronomical units.
And I was given the correct number, which is 0.00001581 light years away,
Yeah.
which is 8.3 light minutes.
8.3 light minutes. So it's 8 divided by, yes, please come up and ask the question. But I gave you the mathematical way to find that number. Please.
What's the closest universe to us?
That closest what?
Universe.
Universe. So the universe is everything. So there is, as far as we know, only one universe.
Oh, what's the closest galaxy?
The
then?
closest galaxy are our satellite galaxies, and the Magellanic Clouds that you can see in the southern hemisphere are 2 of our satellite galaxies. And I don't know how close they are, but I can tell you that tonight you'll probably see Andromeda, and it's about 2 million light years away. So good question. You'll have to maybe travel down to South America or Australia or something like that and see the Magellanic Clouds, and then ask an amateur astronomer down there how far away. Or you can look it up on the internet.
NASA has great sources.
NASA's great. There's a lot of great websites to find astronomical information out. Okay, please. Who else had a question?
What's your favorite nope?
My favorite nope from my conspiracy theories. I like debunking the flat Earth conspiracy theory, only because it teaches us to be a little bit humble, in that we were born on the Earth, and now we're trying to figure out things bigger than the Earth. In order to appreciate the curvature of the Earth, we had to become a space-faring race and get pictures and look back at the pale blue dot, as Carl Sagan called it. And so in order to fully appreciate it, we had to go into space. So we had to go so far away we were in space. That's pretty interesting. You can take a 7-mile bridge, and the 2 towers to hold the cables on the bridge are plumb, and they are radiating to the Earth. In other words, they are not standing parallel, but they're standing a little bit further apart at the top than they are at the bottom, because they are going straight down to a spherical Earth. And they're about, because they are not the full length of the bridge apart, they're only like a couple of miles apart, but still the difference is only in millimeters. Our brain is not going to figure that out just by looking at it, right? We can't tell that difference by looking at it, yet it still is true. We have to go much further away to appreciate the curvature of the Earth. So it helps us stay humble. We were developed here on Earth. We are only going to understand Earth things. We're not going to understand bigger and bigger and bigger pictures without putting a lot of extra thinking in it. So stay humble and put a little bit of thinking into stuff, okay? All right, cool. Good question. Thank you. Anyone else? You can see Saturn pretty good in binoculars. So you don't need a telescope. However, some advantages that we didn't think that maybe we did mention, what I said about the bench and the telescope being stable is very important when you're looking at, because you cannot stay still just unaided. You actually have to brace yourself. When I was actually on the roof looking at the Galilean moons, in order to actually see them with any stability, I had to lay down, brace my arms so they didn't move, and sort of look at it like I'm shrugging my shoulders a little bit and looking at it.
And then drop the binoculars on his face a couple times.
All that, you actually have to learn how to hold your binoculars. If you're using binoculars, hold them at the very end of the binoculars. It's more stable that way than if you try to hold them a little bit closer to your eyes. But yes, with a hobby telescope, you know, in a more inexpensive version, you can see the planets. Well, at least the 5 big ones, very well. But it gets more challenging for dimmer and further objects with a smaller hobby telescope. Was that the question you were asking? Okay, good.
And a little add-on about cheap hobby telescopes. If you are having trouble, do feel free to reach out to us. Facebook, Instagram, we have a Discord server, email, all great ways to reach out to us. There are scopes that are more tailored to a beginner user that are going to be easier for use. There are telescopes out there that are available, like, I'd say department stores, but we don't necessarily have too many department stores left. Your local Walmart might have a telescope, but it might be a little bit misleading and require more setup to get decent views than, but if you are looking for telescope recommendations, we can help you with that later as well.
My opinion on where you should invest. Really young, get a relatively cheap telescope and see where the interest leads. If the interest is maintained, then the views become disappointing quickly for a cheap telescope, and then one more in the range of sub $1,000, but a nice 6 or 8 inch Newtonian you'll start to really see cool stuff at that level, and it's still relatively cheap. Anyone else? Well, thank you, everyone. Let me not hold you back. We have, I think, a couple of observatories. Do we know what observatories are open right now?
I actually don't know. I was going to ask Chris if he knew. But thank you all for coming out. If you want, we also do these free public programs every Saturday, April through October. We have one program this Saturday and one more the Saturday after that. If you want to come to either of them, feel free to do that. The last one of the year, we always invite people to come in costume because it's the last Saturday in October that's closest to Halloween, and it's spooky season. So feel free to come out there. And if you're ever sitting at home wondering what to do on a Saturday night, we do live stream these on both YouTube and Twitch, and we have our old presentations saved on our YouTube as well. So if you go on our website, see a talk that, man, I wish I hadn't missed that, feel free to check us out there. With that, thank you, and good night.
Thank you, everyone.